Yes.
So we are getting into chapter 37, the homework.
Let me begin by doing this, and that will answer your question, I think, quite specifically. I looked at the schedule, decided when we're going to have the two halves of the final, and then I listed the main points for each final, which I think will profoundly assist you in organizing your notes. Both of them are going to be an open notes final, not open book, but open notes. So, the first final will be Monday, May 7th, our regular time schedule, 7:30 to 9:20. And let me list here, mostly it's just names, but a couple of little side topics. For example, the first name I listed, of course, was Einstein. And under Einstein, I mentioned relativity and photoelectric effect. Then came the name Compton. After Compton, I wrote the word Bremsstrahlung and photons and gravity.
What was the first one?
Bremsstrahlung, that German word. Does anybody remember the literal translation of Bremsstrahlung? That's breaking radiation. Breaking radiation, that's Bremsstrahlung. And then photons and gravity, I'm thinking about things like the gravitational redshift and black holes. Now, I guess the rest of them are all just names. I think they're clear and obvious. Here are the names. Rutherford, Michelson-Morley, those are two names, but they go together. Millikan, Frank Hertz, Bohr.
So on the Frank Hertz one, can you be a little more specific on that? Because there's actually a whole lot of ways you can go with that.
All I'm asking about is what is the general purpose of the Frank Hertz experiment. That's all I'm really concerned with. And by the way, I see I see Bohr as a bridge between exam number 1 and exam number 2. Now let's go to the second half of the final, which will be on Friday, the 11th of May, at our regular time slot, 7:30 to 9:20. And most of this will make sense to you, but I have a few comments to make about the last one. So just right now, just take notes, and then we'll talk a little bit more. De Broglie, Bohr, Schrodinger, and right alongside of that, in parentheses, I wrote Schrodinger's cat. Heisenberg, and then the last major category I took was the nucleus. But in parentheses, after the nucleus, in parentheses, I have 3 like subtopics. They are, in parentheses, I wrote 4 forces, maybe 5. Next parenthesis says 5 particles, maybe more. The last set of parentheses are fission and fusion. Now, I'm not going to cover all of those topics on each one of the finals, but I'm going to select from those topics. Those are what I consider to be the top topics in this last section, modern physics. So, you need to organize your notes, and certainly feel free to rewrite your notes and organize them according to the way I've mentioned them here. You can put the little tabs on the side of your note, so you can write Bohr, you can flip the thing open, and all the stuff about Bohr. You might write Schrodinger, and you flip the thing open, and you'll find that some of the Bohr topics fit into the short, but you can write it twice, so that everything related to Schrodinger, whether it be Bohr or de Broglie or whatever, is in that section. So become clever and rewrite your notes, streamline them, put little tabs on there. And I will select from there enough problems that will take me about 30 minutes for each one of the tests. Because I believe that 30 minutes is fair. Since I write the problem, I know exactly what I'm supposed to be thinking. I can solve the problem in 30 minutes. I figure you guys take twice as long or maybe 3 times as long because you have to spend an equal amount of time at first trying to figure out how am I supposed to consider this problem. So I give you 2 or 3 times more time on each problem so that you can sit back and think about it. It should take you a total of 30 minutes of actual calculations and another hour or so of sort of stroking your beard if you don't have one, grow one between them. It should take you another hour of thinking things over, perhaps looking in your notes. But if you're reading your notes too much, you're doing the wrong thing. If you're reading your notes, that means you don't know what you need to know. Your notes are just supposed to be there, perhaps to give you the correct formula and what specific circumstances are which will allow you to use that formula. As you've discovered, especially in this section, it's not just find the formula, stick the numbers. Does your problem match the conditions required for this particular formula? If not, how do you modify the formula? The conditions are not quite like they were in the example problem in class, therefore I have to change the formula a little bit. So that's where I give you a little extra 2 to 3 times more time. Find the correct formula. If it's not in there, then you'll have to modify your existing formula to fit the conditions. All right, so that's kind of a set of broad statements about the 2 exams, final exam 3A and 3B. Just some comments that will help you get your notes organized. And I have a few more comments about nuclear physics here on this last page that I'd like to share with you. Before we do, any comments about the general organization of the problem of these exams? So Monday and Friday this week. Yes, go ahead.
I thought Rutherford and Michelson-Morley were kind of grouped together. I'm sorry, what's the main difference?
Ernest Rutherford, I refer to him as the grandfather of nuclear physics. Rutherford is the guy who discovered the atomic nucleus. Now, we did not talk very much about his experiment, so of course we're not going to be able to question you very much about the details of the experiment. But the fact that he discovered the nucleus and a general description of how he discovered the nucleus is very important. Michelson-Morley, that was a whole different thing, actually. I know it looks similar, but it was actually a totally different thing. I think the Michelson interferometer is an incredibly important research tool which was invented 150 years ago and is still used today in refined versions, and I'm sure for the rest of your career, interferometers are going to be extremely important. Therefore, the Michelson interferometer, what it is and how it works, very important. Go ahead.
On the previous test where it bounced off of yours?
That was when we first talked about it, and then the Michelson-Morley experiment used the Michelson interferometer and essentially discovered that the speed of light is constant in all reference frames, though it was not fully appreciated at the time. It was 20 years later when Einstein theoretically suggested such a thing should be true. And by the way, Einstein was completely ignorant of the Michelson-Morley experiment. It just seemed right to him. That we were able to put together the 2 ideas, the experiment of 1885 and Einstein's paper of 1905 and realized, hey, not only is Einstein correct, but we actually have proof of this 20 years ago. Nobody appreciated it. So the Michelson-Morley experiment really seems to be an important bridge between theoretical physics and experimental physics, especially at the very, very beginning with relativity theory. Okay, good questions. Any others? Yes?
When you were talking about Einstein reading through theories and stuff, ancient theories of light and things like this, and he was putting everything together, you inferred that there was some sort of scientific collaboration of papers and stuff where all these things are published, and you can go to research things. Can you elaborate on that? What is the scientific community with publication, journal, or something?
First, I have to say, golly, we're lucky today because this stuff still exists and you can find it on the internet in minutes. It wasn't too long ago that it was hours of research only at a major university's library could you find this stuff. And what was going on from really the very last part of the 19th century into the first quarter of the 20th century was a whole myriad of discoveries, most of which were completely inconsistent with classical physics, and most physicists were agog by the fact that they believed so profoundly in classical physics they didn't know what to do. But look at, I think the very best spot to talk about the beginning of all of this was in December of 1900, the very first year of the 20th century, when Max Planck discovered a formula to describe the shape of the black-body radiation curve and explained it with the very first quantum ideas. Even though Max Planck at the time was sort of the kingpin of all the physics in the world, even though he suggested that it made him very uncomfortable, the quantum ideas, they made him very uncomfortable, and he said, I simply have to say this in order to derive the equation, but I don't believe it's true. And so that's why I think it took 5 more years after Planck, along comes Einstein and was able to verify that it was true, and that's the whole thing about the photoelectric effect. Planck had one observation that dovetailed with black body radiation. Einstein had a different idea that dovetailed beautifully with the photoelectric effect. And then it was Einstein who said, guess what? This is the same thing. These things called photons exist. Meanwhile, people are trying to understand whether or not atoms and molecules exist. I think you remember that that was the entire passion of Ludwig von Boltzmann, trying to prove these things existed. And Einstein again came along and said, guess what? We've had proof of the existence of atoms and molecules, in this case for 80 years. The so-called Brownian, the paper on Brownian motion. So that also shocked everybody, but they realized it was correct. Hey, we have proof of atoms and molecules Brownian motion. Then people started to try to figure out what these things were all about. The only thing Einstein was able to demonstrate is that atoms and molecules existed and that they were very small. He didn't get a very good estimate of their size. The size of a typical atom is some number of angstroms, and his estimate was a little bit larger than that. But nonetheless, it's a very small object that at the time could never be seen. Therefore, people had to work with them theoretically. And people like J.J. Thomson were guessing at the structure. The only information that Thomson had to go by was, here's these little things, they have a certain amount of mass, and they commonly seem to be electrically neutral, but if you abuse them, you can knock electrons out. And the electrons come out leaving behind an equal amount of positive charge. So they're apparently made of equal amounts of positive and negative charge, and you can knock out electrons. Of course, in classical physics, the electron cannot be orbiting, so he assumed that the mass and the positive charge was smeared out over the entire atom, and that the electrons were stuck in. That's why it's called the plum pudding model of the atom. Of course, it's radically wrong, but at the time, you've got to forgive the guy because he was working with exactly the information that he had. We didn't have very much information. So the J.J. Thomson model of the atom existed for only a couple of years. I think he came up with it in 1906. And 5 years later, Rutherford discovers the atomic nucleus. Now we realize that virtually all of the mass, and certainly all of the positive charges, concentrated right at the center. The electrons are on the outside, and the dilemma comes up again. What are they doing out there? They can't be orbiting because they should be radiating and spiraling and coalescing. 2 more years, along comes Bohr. Bohr suggests, sort of like a rabbit out of a hat, well, if the electrons are in these certain orbits, remember quantized angular momentum, if they're in these certain orbits, then he called them stationary orbits because a stationary electron does not radiate. That was his only way of explaining these things in these orbits and not radiating. So he calls them stationary orbits. The most important thing is he comes out with a perfect theory for everything we already knew about the hydrogen atom. It went further to predict things we did not know. I mean, in particular, the ultraviolet spectrum, which we tested for, and it was there exactly as predicted. So everybody was very celebratory. So 1913, before things start coming together, all of these pieces start coming together, 1913. From 1913 to about 1924, people are wondering about these stationary orbits. It works, it does. You know, it predicts experiments, but stationary orbits, quantized orbital angular momentum, we don't understand what's going on. Here comes de Broglie. De Broglie comes along about 1924, and he says, hey, guess what? Since waves have particle characteristics, remember the photoelectric effect almost 20 years earlier? Waves have particle characteristics, particles should have wave characteristics. And that's all kind of mildly interesting until he calculates the de Broglie wavelength of an orbital electron in a hydrogen atom. And lo and behold, it fits perfectly. You get a standing wave, sort of like a stationary particle. A standing wave is sort of like a stationary particle. And people begin to realize that, hey, this de Broglie hypothesis is pretty interesting. But they discover things like de Broglie waves travel around faster than the speed of light. What are these things? Well, they're not real. These waves aren't real, they're probabilities. But a probability is a measurable thing. So if you square it and you use it to predict the probability of particles in certain orbits or in certain locations or having certain behaviors, it's completely accurate. Schrödinger puts all of that information together and creates quantum mechanics. Stick in there at about the same time Werner Heisenberg, the man who said, everything is probability, nothing is for sure. He comes up with the uncertainty principle. So things start coming together in that area. Then, by the way, once all of that is established, we can begin to investigate the atomic nucleus. We found the nucleus in 1911, but we really started investigating it in the 1930s. What's the size, shape, structure, and particularly what's the behavior of the atomic nucleus? So finally we can get all this stuff and we can put it to work in a brand new field of physics, nuclear physics, 1930. So as a quick answer to your question, that's how I would see the highlights. That's how I would see the highlights. And the rest, what do they say? The rest is history. The rest is history. Good question. Are there others? Let's talk a little bit more about the nucleus, the atomic nucleus. Well, thanks to Rutherford, way back in 1911, we discovered that they're very, very small. If you look at your typical atom, and I'm going to use a capital R, radius of an atom is on the order of an angstrom unit. You look at the nucleus, the radius of a nucleus is on the order of a Fermi unit, 5 orders of magnitude smaller. So the nucleus really is a teeny little thing. This number is a little more accurate than what Rutherford had to work with, but then Rutherford was only doing electronic type collisions. We find in there virtually all the mass of the atom. The mass of a proton is about 2,000 times the mass of an electron, and of course, in most nuclei, there's an equal number of neutrons and protons, so the mass of the nucleus is about 4,000 times more massive than all of the electrons in orbit around it. Electrons are just little orbital pieces of fluff. The nucleus seems to be made of protons and neutrons. So all of a sudden we realize there must be some really strong force. If you were to take two protons and let's say put them 1 Fermi unit apart. So imagine that there's 2 protons here. Can you calculate? Let me ask you just to calculate right now. What would be the expected acceleration?
Would that mean they're like on opposite sides of the nucleus?
That would be like on opposite sides of an ordinary nucleus. And why don't you take just a moment and calculate what would be the expected acceleration for 2 protons 1 Fermi unit apart. In a minute I'll start calculating it on the board. But I'd like you to figure it out. Just imagine you got 2 protons, 1 Fermi.
This was physics 5, again, I can't remember that. This is so early in physics 5.
Oh, they're just full of
Yeah, exactly. Yeah. From physics 5.
10 to the minus 15.
For the force.
I don't know, let me work it out.
Too much acceleration. I didn't calculate the force, I just did the acceleration straight up.
No, that is acceleration.
You got the force, and you know force is mass times acceleration.
Oh, you figured out force, but straight up acceleration.
Oh, you know force is equal to mass times acceleration.
Yeah.
So I didn't calculate the force first, I just used the equation to say the acceleration.
Oh, right. Look at your force and this.
9, you did the 9.
In the 9?
Uh-huh.
Okay.
So what?
What's the mass? 1.6 something times 10
Book.
You have 2 10 to the 9, 9 negative 9. You have 10 to the negative 9, 2 10 to the 9.
And the negative 9 is not correct. Yeah.
Units.
Oh, I see, I was doing that.
That's a little bit different than what I did, but okay.
It's a clean force equation.
766.
Did you guys check the units? I think the units work out just fine.
Yeah, they do.
Yeah.
Page 766. That's what I blame everything on here.
No, that's not negative.
What did you calculate it at?
That's a negative.
It's
It's a negative with difference.
Minus 30,
No, it's not.
that's minus 54. So 10 to the minus 24, is that right?
First of all, it's going to be
I don't think you squared the 1.67, right?
What the?
Say it again?
I don't think you squared the mass of the proton.
Am I supposed to
Well,
square the mass?
No, you don't.
No, but
You just divide it by the
Equals MA.
Yeah, so it's negative 27, which is positive 27.
Oh. Yeah, so I squared that when I wasn't supposed to square that, is what you're saying.
Yeah.
All right, much better, thank you. So I got minus 30, and this comes down as a plus 27, so that is a plus 3. Something strange.
It's a minus. Yes.
yeah.
Yeah.
Negative
What's funky here?
It stays negative, so you add them together.
Yeah. Because you're dividing by it, what's the negative?
30 plus 27.
Yeah. 27 minus 30.
No, no,
27 plus 30.
What, am I doing, what's my funny arithmetic? When this comes down
We
there-
divide that
It
one
stays
by
the
two
same.
by two.
Yeah, that's right, it stays the same, that's what's funky. So is, what are we saying? Minus 30, minus 27, minus 57. Minus
Yes.
57. That's a lot better, thank you. That's a lot better because, let's see. Oh, you're gonna hate this, look. I know you're gonna hate this.
You are?
What?
That cancels with one of those, and that's 10
No, really did not go with it.
Why?
times 10 to what? The 27, 28. So approximately 10 to the 29,
That was close.
right? Is that about what you got?
Yeah.
Probably worked out some fancy number, huh?
Fancy number.
The only point I wanted to make was there's got to be this huge force holding this thing together. Because if there were gravity, perfect, slap it. Because if there wasn't, it's really got a huge repulsive force. So what we've just discovered is that there's a very, very strong force holding these things together. We discovered a new force. So early in the 1930s, we discovered a new force. The new force is the force that holds the nucleus together, called the strong nuclear force. Overwhelms even these huge repelling forces. Then we discover radioactivity. We discover that every once in a while particles escape from the nucleus. How can that be? Well, in the quantum world, we already knew about tunneling. So apparently this force that holds everything together has a certain dimension, which is actually about a Fermi. 10 to the minus 15 meters is the range of the force, and then you get radioactivity because of tunneling effects. But wait a minute, there's new kinds of radioactivity. When they did the study, they found out that there's essentially 3 different particles that are emitted by nuclei. One particle is an alpha particle, later discovered to be a helium nucleus. That's where you can lose a lot of energy and a lot of mass by having alpha particles escape. More about that in just a minute. Another particle is a beta particle. Later on we discovered it was an electron. But wait, there's matter and antimatter beta particles. There is positively charged electrons or negatively charged electrons. And they cannot be explained by the strong nuclear force. They're coming from some other origin. Another new force was discovered by Fermi, and we call it the weak nuclear force, responsible for beta decay. And then the last one is gamma decay. Gamma decay is pure energy. That's where an excited nucleus de-excites. It does not lose any particles, it only loses energy. Just like an electron jumping to a lower state, emitting a photon. A gamma ray is a photon. It just happens to be extremely high energy. Typically something on the order of an MeV. So 1,000,000 times more energetic than an electronic transition. So all of a sudden we discover radioactive decay, alpha, beta, and gamma. Alpha and beta are the nucleus actually physically changing itself, and gamma is just de-exciting itself. So in the 1930s we discovered 2 new forces. We now have a fairly complete understanding of the forces. Gravity, electromagnetic, strong and weak nuclear force. Now, by the way, how is it that physicists understand forces? Have you ever asked yourself that question? Here's 2 planets that are attracted gravitationally. How do they even know they exist? Or 2 protons, they repel each other. How do they know they exist? Are they pushing on each other, but putting their hands out and pushing? No, they're not. The way physicists started to look at these forces was the exchange of particles. The classical example is, imagine you and I standing right here on this smooth surface, perfect roller skates. And we've got one of those exercise devices, I think they're called a medicine ball, aren't they? They're about basketball size, filled with some gelatinous material to be massive, and you get stronger by playing catch with these things. Am I correct? Medicine ball?
Yeah.
Yes.
So we're standing here, we're on this smooth surface, we're both on perfect roller skates, 0 friction. I've got the medicine ball, I throw it to you, of course, what happens to me? I start to coast backwards. As soon as you catch it, you start coasting backwards. When you throw it to me, you accelerate. When I catch it, I accelerate. By exchanging that particle, we create repulsion. Well, that's nice for 2 protons, but what about gravity? You got 2 particles that are attracted. How do you explain that? Oh, it's easy. We just use a different particle. We go back out here, perfect roller skates, only this time we're back to back and I'm holding a boomerang. I throw the boomerang and I start going backwards. You're over here, you catch your boomerang, you throw it, you accelerate, I catch it, I accelerate. By exchanging a different particle, we create attraction. So attraction and repulsion is thought of as the exchange of particles.
So these exchange particles on mass?
They certainly do because they are, well, let me explain it in just a minute, but they certainly do. Now what I'd like to do is I'd like to tell you the name of the particle that exchanges to create each force, and then you'll see the answer to your question. Let's start with gravity. The particle exchange to create gravity is called the graviton. Not yet discovered because it's incredibly weak. As you know, gravity, the force of gravity is something like 10 to the 40 weaker than electromagnetic force, so it's a very painfully weak force. And the graviton is a very subtle object not yet discovered. But the electrical force, the electromagnetic force is carried by the photon. There you go. There's a particle whose mass has already been calculated and measured. So it does have mass. So photons carry the electromagnetic force. The weak nuclear force, oh, you're going to like this name, it's kind of big, very formal sounding, listen. It's called the weak boson. Not bozo, but clown.
Which force is that?
It was named after a fellow whose last name was Bose, a contemporary and a good friend of Einstein's. Everything else was named after Einstein, so they named this particle after Bose. The weak boson. Too many syllables for your typical physicist, so it's been nicknamed now. It's just called the weakon. And here's my favorite. When we were talking about the strong nuclear force, that's a really interesting force. And the particle that makes everything stick together in the nucleus. When they were trying to name it, I suggested the name for the particle should be the Klingon. Because they cling together. But they didn't like that. They said, no, no. The strong nuclear force works like the world's most perfect glue, so the particle is called the gluon. So let me review now. 4 forces, 4 particles. Gravity, graviton. Electromagnetic, photon. Weak nuclear force, the weakon. The strong nuclear force, the gluon. And aside from the graviton, we verified everything else. We're still working on the graviton. It's just too difficult to measure. It's a very subtle measurement. It hasn't been done. Yes?
Does this nullify the field theory altogether?
This explains field theory. Yeah, field theory is not, you know, field of, what do you mean field? Field of what? Grain? What have we got going there? So field theory was used in a very practical way to get answers to questions. And it works beautifully for that. But nobody could establish what a field was. And so instead of fields, they talk about it as particles. So it doesn't nullify, it doesn't replace. But it's more like this is the explanation of what actually causes the force. Field theory is the easy way to get answers. Okay. Interesting thing, ladies and gentlemen. In 1964, 3 men wrote a paper wherein their theoretical physics predicted a 5th particle which did not distinguish between the electromagnetic force and the weak nuclear force. If you're interested, the 3 men's names are Shelton Glashow, Stephen Weinberg, and Abdul Salam. They wrote the paper, published it in, I think, 1964, and it said that actually those 2 forces were actually 2 separate manifestations of a more basic force, which only seemed to exist early in the universe at a temperature of about 10 to the 27 kelvins. We've never gotten that high in any laboratory experiment. That's pretty high. That temperature is higher even than the centers of the hottest stars. Nowhere in the universe today can we create a temperature like that. So nice theory, but we couldn't test it in 1964. In 1983, 2 men got an idea of how to power up the CERN particle accelerator to that temperature.
Build it in Bakersfield?
Let me explain.
Which two forces were that, was that, Professor?
Say again?
Which two forces? Electron.
You got it? Got the answer? Okay, good. Let me explain to you what was going on. You remember the particle accelerators, their energy level is determined by their size. And the CERN accelerator was one of the two really huge ones, 3.2 miles in circumference. And the idea was, well, if we inject protons and antimatter protons into the same accelerator, that accelerator will accelerate the two particles in opposite directions. This will be going clockwise, these will be going anti-clockwise, so that we could have a head-on collision of much higher kinetic energy. Furthermore, when matter touches antimatter, they annihilate each other and turn back into pure energy. So we have two sources of energy. Not only the head-on collision, which is high kinetic energy, you also get annihilation. So by colliding the two, you might be able, just barely be able to reach 10 to the 27 kelvins. And if the Z particle is real, we should find it. This was really kind of fun, though painfully expensive. Because you know what? The detector, probably twice the volume of this room, the detector required to find Z particles was twice as big as this room. We're looking for subatomic particles. Smaller than a nucleus, takes a detector bigger than the room. Cost $10 million to build it. That's nothing. Because where do you get antimatter protons? You don't go down to the drugstore and order a bottle of antimatter protons. You have to make them. So there was a particle, you had to build a new particle ring over here that would manufacture antimatter protons. That was $200 million. This was a major expensive experiment. And yet, it looked like it was going to work. And so, the two men involved were Carlo Rubbia and Simone van der Meer. They sold the idea to the administration of CERN. They spent the money and the time, about a year, building. This was the main construction problem right here. And I think it was late in 83 or maybe early in 84, they fired up their experiment, and lo and behold, there it was. They found the Z particle. The Z particle is real. It's a real particle. And it does not distinguish between two of the four forces, which essentially means that the electromagnetic force and the weak nuclear force actually are just simply two different manifestations of a more simple force that we now call the electroweak force. So the picture in physics got simplified from 4 forces to 3. That rather excited the theoretical physicists, as you might imagine. And so they went back to work on the theory and discovered yet another particle, which I will right now refer to as the exotic X particle, which did not distinguish between the strong nuclear force and the electroweak force. If the X particle is real, then the strong nuclear force is just a separate manifestation of this force, and the universe was being ruled by even more simple forces earlier in its creation. The temperature, however, was about 1 trillion times higher. So if this incredibly expensive experiment led to barely enough energy to create the Z particle, it's taken decades to power up the CERN accelerator, and perhaps they can create an X particle. So that's the state of affairs right now, is we're getting ready to do the experiment, searching for the X particle. It's called exotic now because it's predicted, but we cannot do the experiment yet to test for it.
When did the Z particle, when did they do that experiment?
The Z particle was, I believe it was late 83 that they did the Z particle experiment. And surprisingly enough, this never happens, folks. The very next year, Rubbia and van der Meer received the Nobel Prize in Physics. Normally, any Nobel Prize winning experiment in physics matures for a decade or two. They want to make absolutely sure nobody can find anything wrong with an experiment, right? And so typically, when somebody's awarded a Nobel Prize in physics, it's for work they had done 10 or 20 years earlier. I personally am not aware of any other Nobel Prize that was awarded 1 year after the experiment, except this one Nobel Prize. Kind of fun, I contributed just a teeny little thing to that experiment. I helped them increase their beam density. The problem with this experiment is you get two beams of protons and antiprotons. How likely are they to hit each other? It depends on how dense they are. And I figured out a way to increase the density of the beam. So that was my claim to fame. I got to work on this project.
When you go to CERN?
No, I did it at Stanford. And of course, I had no idea what Rubia and Vandermeer were up to. I say that because they called me on the phone and asked my advice. I chatted with them a few different times on the phone. They used my work, increased the beam density, and did the experiment. I foolishly did not ask them to put my name on their paper. They could write it really small on the back of the last page, but if your name appears on a Nobel Prize winning paper, life is different. I had no idea what they were doing. They just asked for my advice. I gave it to them. And I should have simply, if I had asked, I'm sure they would have put my name on the paper. I say that because don't make the same mistake. If you help anybody do anything, say, just put my name on the paper. Anywhere. You can make it really small. You can put it on the last page. Just put my name on the paper. Okay, so that's the state of affairs. Nobody yet has any idea how gravity fits into this equation, but that's the whole business about string theory. My recollection is we mentioned string theory on Monday, right? So string theory is an attempt to see how gravity fits into this whole picture. Let me check my notes just to make sure I talked about everything I wanted to talk about. All I wanted to mention was 4 forces, maybe 5. 5 particles, maybe more. Now what do I mean, maybe 4 forces, maybe 5? Well, we'll talk a little bit about astronomy, and then I'll mention another force that seems to have just appeared in the last decade or so in our main. Now before we do that, let's finish the nuclear stuff. Now let's talk about the binding energy. What about the energy that holds the nucleus together? It says here, please see page 1153. In your textbook on page 1153 is a very nice example . 1153, you'll notice that this is under paragraph 16.1.5, called binding energy. The example problem is example 36.2. Find the binding energy of a helium nucleus. Compare the binding energy per nucleon with the values in the figure above. Well, ladies and gentlemen, what happens when you fuse a nucleus together is that particles lose mass. You'll see here they talk about it under the binding energy. But the mass of a helium-4 nucleus, which is made of 2 protons plus 2 neutrons, is less than the mass of the individual protons plus neutrons. So when you take 2 protons, 2 neutrons, fuse them together, they lose mass. That mass turns into the binding energy. So all you have to do is find the mass of the individual particles, subtract from that the mass of the nucleus. That gives you delta M, the missing mass. Delta MC squared is the energy, the binding energy. So effectively, if you put that equal amount of energy back into the nucleus, it disassociates back into 4 individual particles. That's the process of fusion. That small particles like protons and neutrons fuse together to build heavier nuclei and release doing. here they show an example of how you do the calculation. You can see it's extremely straightforward. Delta M equals 2 times the mass of a proton plus the mass of an electron plus 2 times the mass of a neutron minus the mass of a helium-4. There's the delta M, there's the missing mass. It turns out to be, look, a fairly small number, 0.03036 U, or AMU in the old school atomic mass units. But you discover for every AMU there is 931.49 MeV per C squared per U. So just multiplying through, you get 28.28 MeV. So the binding energy that holds a helium nucleus together is slightly over 28 MeV, a little bit less than 30 MeV. That's what holds the nucleus together. When you fuse these 4 particles, out comes almost 30 MeV of energy.
That's for helium. That'd be higher for a atom, for a nucleus.
Look at the chart above. It's really pretty interesting where they calculate the binding energy per nucleon. Let me make sure I get the axes the same as he does. So it's A and binding energy. A and binding energy like that. And isn't it interesting, although not completely obvious, the curve is sort of like this, but there's actually a peak at helium. So, so making helium yields the binding energy per nucleon and the A associated with it. So helium-4 gives a little bit of a spike. Helium-4 is a very favored nucleus. It's an extremely tightly bound nucleus compared to other things. That's why alpha particles decay out of the nucleus, because alpha particles are helium nuclei. They're very tightly bound little particles like that. The interesting thing is, this does actually go above that, and then it starts to taper off like that. So there is a point right here where you have maximum binding energy. You know what it is? Iron 56. It's not a coincidence that of the rare elements, and when I say rare elements, I mean things other than hydrogen and helium, of the rare elements, iron 56 is the most abundant one we find around. Why? Because it is the most tightly bound nucleus of all. Anything over here, any mass which is lower than iron 56, will be exothermic as you fuse heavier and heavier elements. It'll be exothermic to here. After here, it's endothermic. After iron 56, to get things to fuse together, you've got to provide extra energy to get them to do it because they're more loosely bound after iron 56. We're starting to saturate the strong nuclear force at iron 56.
Is that like helium goes the iron in the sun?
Say that again?
Is that like hydrogen goes to helium goes to iron in the fusion in the sun?
Well, actually what you find is hydrogens tend to go to helium, and heliums build up. If you look at the more abundant elements, there are always multiples of helium up to iron 56. And so you can almost call these underweight nuclei, and they give you energy by fusing them up to their proper weight. These are overweight nuclei. The only way you get energy out of these is if you break them down to their ideal weight. So it gives me a minute then to say the difference between fusion and fission. Fusion is where you're building up heavy nuclei. I think, it's page 1155. Well, not exactly. But as we're heading towards what I want to talk about, I'm passing page 1155. And I guess I feel compelled to strongly look closely at figure 3613. If you go to page 1155 for just a moment, it'll allow me to go on and finish what I stated here. Here on figure 3613, I'm compelled to point out very carefully, aha, here is the nuclear potential. You'll notice that what they're saying is that the potential of the atomic nucleus is actually a combination the Coulomb repulsion and the strong nuclear force. So let me get the axes just the way he has it in the book here. He has U, potential energy, and R. That's good. So U, here's the potential energy of a particle, R, there's the radius, and there's the Coulomb repulsion, there is the strong nuclear force attraction. So there's the well in which particles sit. If you put protons and neutrons down here, well, there they stay. But if you put protons and neutrons in some of these higher levels up here, notice we have a barrier that can be penetrated. Here's radioactive decay. If a particle is in a state like this, you'll notice that it does not have enough potential energy, it does not have enough energy to get out of the potential well, but there is the possibility of tunneling. So you can get radioactive decay. In this case, I think he's primarily talking about alpha particles, but that's what's going on, these little alpha particles in there. Now, the interesting thing is, if you just take a moment with your expertise, your newfound expertise with Schrödinger's equation and de Broglie waves and so on, you'll notice that he plots a wave function below, which beautifully describes the de Broglie wave of the trapped particle. Now, I would consider it a completely legitimate question to ask you what's going on with that wave. Your answer would be, notice in the well, the amplitude of the wave function is maximum. Once you strike the wall of the well, you have exponential decay. And then once you strike outside of the wall, you go back to an oscillatory function with a much lower amplitude. That says that there is, let me try to get a color like he had, I guess I'll just have to use blue. That says there is a very high probability, let's use this. High amplitude in here means high probability of the particle being found here. And then an exponential decay and a low probability out here. Why? Because it has to tunnel through a relatively wide barrier. So, what does this exponential decay say? It says there is no particle in the barrier, only a probability leaks through. So, we have the probability of finding a particle in the barrier inside, which is quite high. We have a probability of finding the particle outside, which is low. There is no chance of finding the particle in between, but the probability decays on its way through. So this is the same basic idea that we've been talking about. We would not expect you to solve Schrödinger's equation for a well like this, but if you saw the well and you saw this wave function, you should be able to explain the wave function. Why does it oscillate here with a high amplitude? Why does it oscillate there with a low amplitude? Why does it not oscillate in between? What would you expect to see if I chose, instead of this energy level, that energy level?
Higher amplitude waves on the outside.
A lower high amplitude here, a higher low amplitude there, and less of a decay. Is that what you said?
Yes.
That's exactly right, because you have, you're now, it's not as high and it's not as wide. So there's going to be a higher probability it leaks through. So those are the kinds of questions I would feel would be legitimate, not write the wave function for this thing. That's sort of above and beyond the Call of Duty. But explain it, there it is, explain it, explain what's going on. You need to remember oscillatory means there is a particle. If it doesn't oscillate, there is no particle. High amplitude, high probability, low amplitude, low probability. Those are the kinds of things I'd be looking for in an explanation. Okay, I didn't want to skip that. I thought this was a very, very nice little chart, and I think you guys are well equipped to describe it after we did all that, had all the fun we had with Schrödinger's equation. Now, where's the next one here? 1167. For those astronomers within this group here, on page 1167, they're talking about what stars do to make energy. The upper cycle here is called the proton-proton gate, page 1167, under paragraph 36.3.2, energy generation in stars. The first one, proton-proton cycle, that's how our sun produces most of its energy. A lot of stars produce most of their energy by this process. Notice that it's a three-step process that fuses hydrogen into helium. Some stars, our sun does a little bit of what's called a CNO cycle. And notice that's a, what is it, a 1, 2, 3, 4, 5, 6-step process. Very complicated, very much more complicated process. But still, fusing hydrogen into helium. That's how stars make their money. That's how stars make their money. By fusing hydrogen into helium. And by these two processes and others. I think you're well aware that there's a process called fission. It is the other side of this graph, ladies and gentlemen. If you have overweight nuclei, let's take, for example, uranium nuclei. They tend to be overweight. If you fission them, that is, break them apart, then you go from more loosely bound nuclei to more highly bound nuclei. That means you're going to get energy back by breaking them apart. So iron-56 is sort of the target. If you're down in this area, you gain energy by fusing towards iron-56. If you're in this area, you gain energy by fissioning back towards iron-56. And that process was, of course, the first process that we harnessed as nuclear energy. We discovered that U-235 is a very interesting process. On page 1169, they're showing what goes on. That if you have a uranium U-236 nucleus, it has a real interesting form of instability. It's got a strong skin of the strong binding force holding it together. But there are so many protons in there, it's almost stretched the binding energy to its maximum. And it looks like the nucleus shakes and vibrates and quivers. And it has a resonance mode